Welcome to the Deep Dive. Today, we are tackling a topic that, well, it really defines the next century of building. This incredibly urgent global challenge of sustainability in the built environment. As the USA grapples with, ambitious net zero targets and these extreme weather events we keep seeing, the architecture, engineering, and construction industries, the AEC sector, they're realizing the need for radical transformation.
A complete shift.
Exactly. And that change agent, it isn't some new kind of low-carbon concrete, surprisingly. It's artificial intelligence.
That's really the core of our exploration today, isn't it? We're diving into how AI is fundamentally changing the calculus of design. It's moving us beyond just, simple energy efficiency.
Right, the basic stuff.
And toward genuine carbon reduction goals. Our source stack for this is pretty comprehensive. It's a mix of architectural analysis, some deep dive technology reports on machine learning applications, and also some very specific real-world project case studies. We're looking at examples from North America, but also major global hubs, too.
So our mission today, it feels critical. We want to unpack how this powerful fusion of AI and building information modeling BIM is achieving something pretty much unprecedented. It's moving high-performance, sustainable design, which used to be this expensive, exclusive luxury feature, right? Reserved only for those landmark flagship projects.
The big statement buildings.
Yeah, exactly. And it's moving it towards becoming a standard, cost-effective requirement. So this deep dive, it should illuminate the real-world impact of this shift, on the efficiency of our cities, the economics of housing, and crucially, the specific professional skills you need to stay relevant in this rapidly transforming field.
Absolutely.
Let's start with why AI isn't just sort of helpful, but maybe absolutely imperative right now. Okay, let's kick off with that fundamental transformation you mentioned in the AEC sector. I mean, for decades, sustainability was treated almost like a secondary problem, wasn't it?
Oh, completely. Often relegated to a specialist consultant, someone who came in late in the design process.
Right, near the end.
To just kind of tweak the specs, maybe check some boxes to ensure the building achieved an LED certification or something similar. That sequential process, it made deep energy optimization really difficult and, frankly, often very expensive.
So AI flips that?
AI flips that entire script, yeah. It basically enforces sustainability as a central priority right from the very beginning, from the earliest conceptual massing stage. And the reason this works is because AI provides this technological toolkit that humans, well, we simply can't compete with it in terms of sheer scale and speed. We're talking about the convergence of advanced data analytics, sophisticated machine learning, ML, and predictive modeling.
But, okay, what's the specific mechanism there? Because we've always had energy modeling software, right? What does the machine learning part enable that, say, traditional simulation software couldn't really do?
That's a great question. The difference really lies in the iteration and the complexity of the input data. Traditional modeling is largely rule-based. You input specific values, it calculates an outcome, simple cause and effect.
Got it.
AI, particularly ML, allows for real-time iterative simulation across literally thousands of scenarios simultaneously. It can take messy, unstructured data like hyperlocal microclimate data, historical occupancy patterns, material properties, and it generates optimized design options that can dramatically reduce energy use.
So it's handling way more variables at once.
Exactly. It allows architects to explore the entire design solution space almost instantaneously. It identifies these optimization possibilities that, would have taken a human team weeks, maybe even months of tedious manual calculation before.
Wow. And the measurable impact of that speed. This sounds pretty astonishing. The numbers we pulled from the AC Summer Study, they estimate that AI-driven optimization could help reduce overall energy consumption and building emissions by, well, a substantial 8 to 19% globally.
That's right. And we should probably clarify what that 8 to 19% reduction really means.
Okay.
We're primarily talking about operational carbon, so the energy consumed throughout the building's life for heating, cooling, lighting, all that stuff.
The day-to-day running.
Precisely. That's kind of the low-hanging fruit where AI really excels because it can dynamically optimize the mechanical systems. But the precision AI offers is also vital for starting to address embodied carbon.
The upfront carbon cost of the materials themselves.
Exactly. The carbon footprint of the materials, their extraction, transport, manufacture, the whole life cycle. The speed and precision that AI brings to both of these spheres is just absolutely vital if we're serious about meeting ambitious global carbon reduction and net zero goals within the, frankly, narrow time frame we have available.
Right. That speed also drives a crucial economic consequence. what we're calling the democratization of sustainability.
Mm.
You mentioned earlier that high-performance design was historically sort of a premium service. Why was it so expensive back then, and how does AI actually solve that cost barrier?
Well, it was expensive because it required highly specialized expertise.
Yeah.
You needed consultants who had, proprietary knowledge, expensive software licenses, often tools that didn't even talk to each other easily.
Right, interoperability issues.
Big time. So for a small firm designing, say, a standard commercial building, hiring that level of consultancy for every single project was simply not viable. They'd focus on meeting the basic code, not pushing for optimization.
So the analysis itself was the real cost bottleneck.
Exactly, that was the barrier. But now we have these cloud-based AI tools, things like Autodesk's generative design functionality built into their platforms, or dedicated platforms like Cove.tool.
Okay.
These platforms have essentially packaged decades of high-end energy and environmental analysis expertise into an accessible, often subscription-based service. They automate the routine calculations, run complex environmental performance tests in the background while the architect is still sketching.
So it's happening almost in real time as they design.
Pretty much. This makes that high-end analysis accessible even to small architectural practices, maybe even sole practitioners sometimes. By standardizing environmental accountability, making it cheap and fast, sustainability is no longer just reserved for those large, signature glass towers in major cities. It starts to become the expected standard for every structure built, which is a huge shift.
That sets the stage beautifully. Okay, let's pivot then to the mechanics. We've established AI is involved right from the start, but where exactly do architects, plug AI into their actual process to make buildings greener? Our sources seem to identify 5 crucial areas where AI optimizes across the entire building lifecycle.
That's right. The first one, and arguably the most immediate application, is design optimization. This is really where AI algorithms process these incredibly vast data sets. Things like site topography, detailed solar paths throughout the year, prevailing wind directions, even existing urban shading from nearby buildings.
Okay.
And it uses all that to suggest the most efficient design options right from the get-go.
I get the general idea of optimizing the footprint, but can you
Yeah.
give us maybe a concrete example? Like, what specifically is AI optimizing there that maybe a human wouldn't catch or wouldn't catch as easily?
Certainly. Let's take a commercial high-rise in a dense urban environment like downtown somewhere. A human designer might spend, I don't know, a day calculating the optimal building orientation and maybe the window-to-wall ratio based on, say, peak summer solar heat gain.
Right, a key metric.
Definitely. An AI, however, will manipulate the building's massing, its facade geometry, the orientation, maybe hundreds, even thousands of times in just minutes. It's specifically tuning the design to maximize beneficial daylighting penetration in winter while simultaneously minimizing unwanted solar heat gain in summer.
So it's balancing competing needs.
Exactly. It focuses intensely on optimizing the building envelope, the skin of the building, to reduce the dependence on mechanical systems like HVAC right from the very first sketch. It's a complex, multivariable calculation, constantly seeking the highest performance across those competing requirements.
So it's not just finding a good solution, it's finding perhaps the best possible compromise solution across dozens of constraints.
Precisely. Which leads us directly into the second key area, advanced energy analysis. AI-powered systems perform modeling that moves far beyond just simple peak load calculations. They assess complex, really granular needs, like dynamic HVAC loads that change throughout the day, lighting demands based on real-time occupancy prediction.
Not just assuming full occupancy all the time.
Right. And optimal insulation and glazing strategies based on microclimate data.
What's the real difference between this and, say, running a standard energy simulation in a BIM tool like Revit? We've been able to do that for a while.
The difference is sophistication and scope, mainly. While traditional software can definitely calculate energy use based on defined loads that you input,
Yeah.
AI incorporates machine learning to actually predict future loads based on learned behavioral patterns and environmental patterns over time.
So it learns from the building's context.
Exactly. For example, it doesn't just calculate the needed HVAC load for a typical hot summer day. It predicts, based on historical weather data and learned occupancy, how the thermal mass of the building will interact with predicted hourly cloud cover changes and the building's specific usage profile for that day of the week.
That's incredibly detailed.
It is, and this depth of analysis is crucial because it helps ensure buildings can meet really rigorous green certifications. Things like LEED Platinum, BREEAM Outstanding, or the WELL building standard right from the initial concept phase. This avoids the highly costly process of having to redesign systems later on to meet those targets.
That sounds incredibly powerful, especially when we start talking about the third area, smart material selection. Materials are just so critical because they represent often the lion's share of that embodied carbon we
A
mentioned.
huge part of it.
How does AI manage the complex supply chain logistics and data needed for truly sustainable material choices?
Yeah, this is a major area of growth and, frankly, complexity. AI tools are starting to utilize sophisticated life cycle assessment LCA databases. These databases catalog the embodied carbon of thousands upon thousands of materials.
Right.
So a human designer might choose, say, a local brick because intuitively it feels sustainable due to reduced transportation miles.
Makes sense on the surface.
It does. But AI will go much further. It calculates the exact carbon footprint of that specific local brick, considering its manufacturing process, compares it to maybe a high-performance recycled steel panel shipped from 500 miles away,
Okay.
and determines which choice actually offers the lower overall life cycle impact. It considers factors like durability, maintenance requirements over decades, and importantly, the material's end-of-life plan. Can it be recycled or reused?
That material selection piece is critical for achieving circularity, right? Where materials are reused rather than just ending up in landfills. I imagine tracking all those materials across a complex global supply chain is a massive data challenge.
It is absolutely enormous. And AI is really the only practical way to effectively manage it at scale. It aids in identifying low-carbon materials, locally sourced options where they genuinely make sense, or truly circular materials by linking the selection process directly to global supply chain data, embodied carbon databases, even things like environmental product declarations, EPDs. This focus on measurable reduction in construction waste and overall carbon footprint requires tracking materials from cradle to cradle, or even cradle to grave, realistically sometimes. It's a feat of data synthesis that machine learning is uniquely suited to handle.
Okay, the fourth crucial area moves us out of the individual building itself and into the wider context: urban planning and site analysis.
Yes, and this is where AI truly demonstrates its capacity for complex synthesis, bringing multiple layers together. Algorithms evaluate massive environmental datasets. We're talking floodplain maps, zoning laws, public transport proximity, complex local weather patterns, air quality data,
All layered on top of each other.
all layered.
Yeah.
And it uses this to determine optimal building locations and even entire neighborhood layouts for maximum energy savings across the whole development, not just optimizing one building in isolation.
And we're seeing this in action already. You mentioned earlier the work at Thomas Jefferson University's Institute for Smart and Healthy Cities, where students used analytical AI tools like Forma.ai. Can you tell us a bit more about what that specific tool allows them to analyze beyond just simple solar gain?
Yeah, Forma.ai and similar tools like it are powerful because they incorporate real-time environmental physics into the early design stages for those Philadelphia interventions the students were working on.
Right.
The AI modeled things like complex wind flow patterns around proposed structures. That's essential for mitigating the urban heat island effect, which is a huge issue in cities. It also modeled localized noise pollution propagation.
Okay, so not just energy, but quality of life factors too.
Exactly. Instead of just creating a static 2D urban map, the students use AI to conceptualize really dynamic changes. For instance, the idea of turning the Vine Street Expressway into a giant green park.
Which sounds amazing, but challenging.
Totally. But the AI helped validate the concept. It showed how this transformation could significantly improve fresh air circulation in the area and positively impact the thermal environment for surrounding structures. This directly contributes to greener infrastructure and, ultimately, a higher quality of life. The student concepts explicitly prioritize light, greenery, and improved microclimates over just standard car-centric bulk construction approaches.
That's fascinating. Finally, the fifth area shows that AI's impact is continuous. It extends far beyond design and construction into predictive maintenance and operations.
Absolutely. This is critical because a building's operational life spans decades, right? And performance drift, where the building gradually becomes less efficient than its original design intent, is a really serious and common issue.
Things break, systems degrade.
Exactly. So, post-completion, AI systems can monitor performance in real time, often integrating directly with the building's Internet of Things, IoT sensors. They track everything from the exact number of people in a specific room using occupancy sensors to the minute-by-minute performance of the HVAC system, energy consumption, water usage.
The constant stream of data.
A constant stream. This allows the AI to dynamically adjust energy use based on actual need, not just schedules. It can also predict equipment failures before they happen by detecting subtle anomalies in performance data.
Preventing downtime and waste.
Precisely. And optimizing the building's green performance throughout its entire operational life, ensuring those projected energy savings and operational costs are actually met or even exceeded over the long term.
Okay, so we've established AI's power in analysis, optimization, predicting performance.
Yeah.
But as you alluded to earlier, AI doesn't just analyze abstract data points. It analyzes the digital model of the building itself.
Yeah.
And that's where building information modeling, or BIM, comes in so crucially. For anyone listening who might be less familiar, BIM is much more than just a fancy 3D model, right? It's really a central, shared digital repository for all project data, geometries, costs, construction schedules, material specifications, everything. It's the structured data backbone of the entire project.
Absolutely. It's the single source of truth, ideally. And the fusion of AI and BIM, that's the real engine driving this transformative efficiency we're talking about. If BIM is the structured data library, AI is the intelligence that processes and learns from that library.
Okay.
This integration allows for genuine real-time analysis. When AI ingests the structured data directly from the BIM model, it can instantly calculate the resulting energy consumption, the daylight optimization, the structural load implications, even the cost estimations of a proposed design change someone just made.
So the feedback is immediate.
Immediate. This really tight feedback loop ensures constant alignment with sustainability goals and, just as importantly, drastically reduces design errors. Because optimization isn't something you check at the end, it's inherently built into the design process, not bolted on afterward.
I want to challenge that just slightly, though, because BIM itself has always allowed us to model these variables, right? You could change a wall type in Revit and see the U value change. What specifically does AI add to that BIM environment that the internal calculators maybe couldn't handle effectively, say, 10 years ago?
That's a really crucial distinction to make. Yes, traditional BIM tools could calculate the effect of a change after the human designer initiated that change.
Right.
What AI introduces is an autonomous layer of intelligence and, critically, iteration. It shifts the capability from merely calculating the effect of a change to actively generating the best possible change, or multiple options, to meet a defined performance goal set by the designer.
So it proposes solutions, not just validates inputs.
Exactly. And the combined tools, AI plus BIM, can simulate how a building will perform not just based on fixed day-one parameters, but how it might degrade or optimize over decades under varying future conditions, like changing climate scenarios or different usage patterns. This helps stakeholders make really critical, informed decisions that reduce long-term life cycle costs and environmental impact in a way static analysis never could.
And this leads directly to that massive leap in speed we're seeing with generative AI in the workflow.
Absolutely. Generative algorithms are speeding up those earliest design stages enormously. Think about the early massing and volume studies historically. These were really time-consuming.
Yeah, lots of sketching and basic models.
Right. An architect had to manually sketch different options, model them crudely in 3D, maybe do some basic calculations on floor area ratios, setbacks.
Lots of back and forth.
Lots of back and forth. Now, the architect defines the high-level constraints and the desired performance goals. Here's the site boundary, here's the environmental context from GIS data, here are the local zoning regulations, we need this many units, we can't exceed this level of solar heat gain.
Setting the rules for the AI.
Exactly. You set the rules and the goals. And the AI rapidly generates numerous viable design options that fit those constraints, often scoring them immediately based on the defined performance metrics like energy use intensity or daylight autonomy.
That truly is a paradigm shift, isn't it? It changes the whole front end of design.
It really is. The design workflow is no longer purely sequential, step A, then step B, then step C. It becomes rapid, creative, and highly iterative. We've seen case studies, like firms using tools such as Autodesk Forma, reporting they've cut those laborious volume studies, which often took maybe 2 days of focused manual modeling, down to just 1.5 hours.
2 days to under 2 hours.
Yeah, that doesn't just save time, obviously. It ensures that by the time the human architect starts refining and detailing the design, they are starting from a fundamentally optimized form factor. That saves potentially hundreds of hours downstream in tweaking and fixing inefficiencies.
That huge time saving seems directly related to the evolution of modeling itself. We've discussed parametric modeling for years in architecture, right? This idea where you establish algorithmic connections between the different parts of a structure, change the grid spacing, and the columns automatically adjust.
Correct.
But as you said, traditional parametric modeling, while powerful, required extensive manual labor to actually define all those intricate algorithms and relationships.
That's right. It was powerful but brittle and time-consuming to set up. AI injects a layer of dynamism into that parametric framework. It transforms the parametric model from a set of fixed rules into dynamic, real-time simulations. Instead of just static relationships, the design can dynamically adjust based on changing external data inputs. Maybe it's real-time weather fluctuations pulled from an API, or newly enacted urban development trends affecting site density, or even adjustments in material cost boundaries from supply chain data.
So the model learns and adapts.
In a sense, yes. This iterative, data-driven adjustment capability leads to far more precise predictions regarding energy performance and even structural integrity than ever before because the model is constantly refining itself based on the latest information.
Let's get concrete for a moment by naming some of the platforms that are driving this. For developers focused specifically on rapid, regulatory compliant housing, the platform Architectures seems fascinating.
Yes, Architectures is a prime example of generative AI focused squarely on the often highly regulated world of residential developments.
Right. Lots of rules there.
So many rules. It optimizes feasibility studies and regulatory confidence checks in literally minutes. A developer can input a site boundary, maybe a required number of housing units, target demographics, and the AI will rapidly propose multiple layouts that meet complex requirements like parking minimums, setback distances, fire escape routes, daylight access rules for each unit.
Things that used to take ages to verify.
Exactly. And crucially, it instantly provides standardized BIM models in the Industry Foundation Classes IFC format. That's the open standard. So the AI's output can flow seamlessly into the traditional architectural workflow using standard BIM software.
We've also mentioned Autodesk Forma a few times now. That seems positioned as a top solution for real-time sustainability assessments and broader urban planning analyses.
That's right. Forma focuses heavily on that upfront contextual analysis we talked about earlier, bioclimatic analysis, wind studies, noise pollution, solar access, all integrated right at stage 0, the very beginning of the project.
Okay, and then there's this concept on the horizon, virtual assistants representing maybe the next leap in accessibility. You mentioned BIM GPC. What does that actually mean?
Yeah, think about a really large, complex BIM model for, say, a hospital or an airport. It holds millions, maybe billions of data points.
Overwhelming amounts of data.
Totally. BIM GPT represents the idea of a specialized AI system, likely based on large language models, that can interpret natural language questions about that model. So not just standard database queries, but complex conversational questions like,
Give me an example.
what is the total embodied carbon footprint of all the non-load-bearing partitions on the 5th floor of the West Wing? And how would that change if we swap them out for locally sourced gypsum board with X recycled content?
Wow, okay. That's complex.
Very complex query. But the AI could potentially parse that, query the relevant data within the BIM model, material quantities, EPZ data, location data, perform the calculation, and give you an answer in plain English. This capability could streamline data retrieval dramatically for all stakeholders, project managers, clients, facilities managers, democratizing access to complex BIM data even for those who don't have specialized BIM software expertise or the time to dig through the model manually.
That really lowers the barrier to using the model's intelligence.
Okay.
This is where the rubber really meets the road, I think. This isn't just theoretical potential anymore. We are seeing landmark projects across the USA actively using AI right now to manage and optimize sustainability.
Absolutely. We can start with a great example of operational AI intelligence, using AI after the building is built, the Edge in Seattle. Now, this isn't a brand new building, but its performance standards are constantly being refined by AI. It functions as this incredibly innovative office building that leverages AI for real-time dynamic energy management.
So how does the AI actually learn to manage the energy use in a place like the Edge? Is it just pre-programmed rules?
No, it's much more dynamic than that. It relies on a dense network of literally thousands of sensors embedded throughout the building in lighting fixtures, HVAC components, even furniture, sometimes tracking lighting levels, CO2 concentrations, temperature, humidity, and critically real-time occupancy. The AI system learns the behavioral patterns of the building's inhabitants over time. It figures out when certain floors are busiest, how many people typically use the cafeteria at lunchtime, how the building's thermal mass reacts to temperature shifts throughout the day and seasons.
So it builds a predictive model of the building's use.
Exactly. It uses this historical data combined with real-time inputs to dynamically predict energy needs, often an hour or more ahead. This allows the building to proactively adjust ventilation rates, dim lights in unoccupied areas, pre-cool spaces before peak occupancy, all
Right.
dynamically.
And the result.
Significant demonstrable energy savings and reduced operating costs compared to a conventionally managed building. It ensures the building is constantly performing above its baseline efficiency targets, adapting to actual use patterns day by day.
Okay, another Seattle example, maybe even more famous, is the Bullitt Center. It's
Right.
often cited as like the pinnacle of green construction, right?
Indeed it is. It's often referred to as the greenest commercial building around the world, partly because it aimed for the incredibly rigorous Living Building Challenge standards. The focus there was on achieving net zero energy consumption, net zero water use through rainwater harvesting, and heavy integration of on-site solar power.
So how does AI fit into a building that's already designed to be hyper-efficient?
Well, the Bullitt Center leverages AI-enhanced building management systems, BMS, to continuously monitor every aspect of energy and water use with extreme granularity. The AI acts almost like a digital guardian or custodian for the building's performance goals.
No.
It's constantly cross-referencing real-time performance data against the strict net zero targets. So if the solar array production dips unexpectedly due to cloud cover, or if water consumption in a particular zone exceeds a predefined threshold, the AI flags it immediately. It might suggest or even automatically implement adjustments to mechanical systems or alert facilities managers to investigate potential issues, ensuring the building's hyper-efficient design stays hyper-efficient over its entire lifespan. It prevents that performance drift we talked about.
Got it. Moving down the coast, we have what sounds like a perfect, really practical example of AI combining sustainability with affordability goals. The Phoenix in West Oakland, California. This is a 316-unit sustainable housing development being built on the site of an abandoned steel factory, right? A brownfield site.
That's right. And the goals there were extremely ambitious and often seem contradictory. The team aimed to build these homes for roughly half the traditional construction cost and in half the time, while also achieving a massive reduction in carbon footprint compared to typical Bay Area multifamily complexes.
Wow. That combination speed, low cost, and high sustainability that usually seems impossible in construction. Pick two, maybe.
Exactly. It's the classic triangle problem. How do they manage it? Well, the secret, according to the reports, lay in the intense early-stage design optimization led by the architects, MBH architects, using AI-powered
One
tools.
specifically.
They use generative AI techniques to rapidly prototype and evaluate different structural and material systems very early on. For example, they were able to test dozens of different structural layout options, comparing the detailed cost implications, the construction schedule impact, and the embodied carbon footprint of using, say, conventional wood framing versus prefabricated modular units versus maybe light gauge steel framing, all in near real time.
So they could quickly compare very different approaches.
Very different approaches, very quickly. The AI allowed them to rapidly discard the options that were clearly non-viable because they failed on either the cost target or the carbon metric, or both. This AI-enabled rapid iteration reportedly reduced the foundational design time for figuring out the core structure and layout from what might traditionally take maybe 2 weeks down to a mere 6 hours.
2 weeks to 6 hours. Incredible.
It is. And that massive productivity gain translates directly into reduced project costs and, crucially, faster construction starts, getting needed housing built quicker.
This seems to feed into the wider urban influence of AI-driven design that we've sort of observed bubbling up. While it was controversial, the concepts pioneered by Google Sidewalk Labs for their proposed smart district in Toronto, they seem to have heavily influenced urban design thinking across the U.S., even though that specific project didn't proceed.
That's a fair point. What Sidewalk Labs really emphasized, which has since been absorbed into a lot of mainstream urban planning thinking, was the critical need for data-driven, holistic planning at the neighborhood or district scale.
Right, looking beyond the single building lot.
Exactly. They used vast data sets and predictive modeling to conceptualize neighborhoods that could maximize energy efficiency through shared systems, enhance green spaces intelligently, and create genuinely climate-resilient communities. They looked at things like real-time traffic flow optimization to reduce congestion and emissions, dynamic waste collection based on sensor data, highly efficient district energy systems.
So even though the Toronto project faced headwinds, particularly around data privacy and governance,
Big headwinds, yes.
the underlying principle using AI to plan for optimal resource distribution and environmental performance at the city scale, that idea seems to be taking root.
I think it is. It's now becoming a core element of how forward-thinking U.S. cities approach new climate initiatives, infrastructure planning, and resilience strategies. Using data and AI to understand the complex urban system is becoming standard practice.
Okay, this whole discussion, it inevitably leads us to that common anxiety, doesn't it? If AI is getting so good at optimizing testing options, even generating initial designs, does it eventually replace the human architect?
It's the elephant in the room, for
Yeah.
sure.
But based on our sources and what
Mhm.
experts are saying, the answer seems to be a pretty resounding no but, and it's a big but. It requires a dramatic shift in focus for the architect. AI becomes more like the hyper-efficient technical partner.
That's absolutely the critical takeaway. AI's primary role, at least for the foreseeable future, is to free human capital. It excels at automating the most repetitive, often tedious, low-value tasks.
Like what specifically?
Think about the countless hours architects and designers used to spend on things like manually drafting minor elevation changes, meticulously calculating code compliance checks across multiple overlapping jurisdictions, or generating dozens of slightly different 3D model iterations just for a client review meeting.
Yeah, the grunt work.
The grunt work. AI can consume those hours, frankly. This frees up architects and designers to focus on the high-value skills where humans are, and likely always will be, indispensable. Genuine creativity, emotional intelligence and understanding client needs, strategic communication, complex non-technical problem solving, ethical judgment.
The uniquely human skills.
Exactly. And this shift isn't just theoretical, it's already in motion. Recent surveys indicate that over 40% of architectural firms, especially larger ones, have already begun integrating AI tools into at least some parts of their conceptual design or analysis workflows.
And we are definitely seeing high-profile designers using some of these newer AI tools like text-to-image generators, ChatGPT with DALL-E, Midjourney, LookX, not necessarily to produce final construction drawings, but for initial concept generation and visual inspiration. It's becoming part of that iterative idea generation workflow.
Absolutely. The best, most forward-thinking firms are actively leveraging this power. Take Zaha Hadid Architects, for example. Their principal, Patrick Schumacher, has publicly discussed how they use image generation AI to rapidly prototype initial concepts. Their work is famous for its incredibly complex, flowing, non-standard structural geometry.
Their signature style.
Exactly. The very kinds of forms that are notoriously labor-intensive to model, visualize, and test using traditional methods. AI helps them quickly generate a wide range of visualizations and forms that align with the studio's distinct aesthetic, allowing them to explore far more options and refine those complex geometries much faster than any human modeling team could realistically manage.
Or there was that example from the firm Hickok Cole. A project architect there, Jack Lynch, apparently used the AI chatbot ChatGPT not just for visualization, but to actually generate the initial programmatic brief, the list of requirements for a hypothetical 24-floor mixed-use building concept.
Right.
And then he used Midjourney to visualize the resulting concept described in that AI-generated brief.
That combination is really potent, isn't it? Because it shows AI operating on both the analytical constraints-based side, generating the program brief, and the creative visual side, generating the image. It allows the human designer to kind of jumpstart a project with a rich set of initial constraints and compelling visual stimuli almost immediately.
Yep.
We also saw examples like the work of Manas Bhatia, an architect who used Midjourney to develop these really stunning, almost fantastical representations of structures designed to truly coexist with nature buildings that appear to grow out of forests or blend seamlessly with geological formations.
Beautiful images.
Beautiful, thought-provoking images. This illustrates AI's power not just in optimization, but in stimulating completely new architectural forms and ideas that challenge our conventional construction paradigms. It's an inspiration engine.
Okay, so AI is clearly a powerful idea generator and optimizer. But what are the current really crucial limitations of AI that we absolutely must maintain critical awareness about? It's not magic.
No, definitely not magic. And we must be very clear about this. AI systems, as they exist today, operate without any inherent sense of feature relevance or priority systems based on actual human experience or values. They are fantastic at optimizing for clearly defined, quantifiable constraints, lowest cost, minimum carbon, maximum floor area,
The numbers.
the numbers. But they are purely prompt-driven and advisory. They lack the innate ability to be a storyteller or to respond meaningfully and sensitively to the specific historical context, the cultural nuances, the community needs, or the complex emotional requirements of a particular site or project.
Meaning, if you just ask an AI to optimize purely for, say, housing density, it might give you a ruthlessly efficient, massive, monolithic block that completely fails at creating a sense of place, community, or frankly, beauty.
Exactly that. AI, as currently constituted, has not been programmed for and maybe cannot be programmed for the specific, nuanced, ethical, or contextual brief that defines high-quality, truly humane, long-lasting architecture. There remains a fundamental disconnect between generating a spectacular, perhaps fantastical visual concept in minutes using Midjourney,
Right.
and actually materializing a sensible, buildable, durable structure that includes rigorous compliance specifications, certified material warranties, long-term performance guarantees, and meets the real needs of the people who will use it. The architect remains the absolutely necessary bridge between that digital possibility and the complexities of material reality and human need.
So this powerful technology is clearly driving sustainability forward in many ways. But as we look ahead, the roadmap isn't entirely smooth, is it? The sheer speed and scope of this AI revolution seem to introduce some pretty significant systemic challenges that we really must address head on.
Absolutely. We need to acknowledge the immediate ethical and social hurdles. The first big one is design bias. AI tools are only as effective and as unbiased as the data they are trained on.
Garbage in, garbage out.
Essentially, yes. If that training data pool lacks diversity, if it inadvertently favors certain popular aesthetic trends, or if it's optimized solely for one climate zone, say cold northern European climates over another, like hot and humid climates found in parts of the US,
Right.
then the resulting designs generated by the AI can reflect and even amplify those biases. This could lead to buildings that are non-optimal for their actual location, or even culturally inappropriate. The responsibility really falls squarely on the human architect to critically evaluate the AI's output, recognize these potential algorithmic biases, and actively correct for them.
Okay, what else?
Secondly, there is the undeniable risk of over-reliance. If the industry starts to excessively rely on automation for routine design decisions, maybe just accepting the first optimal solution that AI spits out.
Yeah, the path of least resistance.
Exactly. We run the risk of limiting genuine human creativity and discouraging the exploration of truly novel architectural design principles that might fall outside the AI's current training parameters. We need human curiosity and intuition to push beyond the AI-suggested optimum sometimes.
Makes sense.
Third, related to the automation point, although we focus on efficiency gains, the concern about job displacement, particularly for entry-level roles, those historically focused on drafting, detailing, basic modeling, that concern persists. It means firms need to develop clear strategies for upskilling their junior staff, transitioning them into roles focused on managing AI tools, curating data, and applying critical judgment to AI outputs.
And then there's a really critical, almost self-inflicted environmental challenge here.
Hmm.
The energy paradox. You mentioned this briefly. Generative AI's intensive energy demands actually pose a significant challenge to the very global greenhouse gas reduction goals it's trying to help solve.
It's a major irony, isn't it? We're using massive amounts of computing power to design greener buildings, but that computing power itself comes at a significant environmental cost.
How significant?
Well, it's widely acknowledged now that data centers supporting large-scale generative AI training and ongoing inference are far more energy-intensive than traditional IT infrastructure or standard cloud computing centers.
Okay.
They're often geographically located where they can intersect with key internet fiber optic nodes and, crucially, access large amounts of reliable electricity, which isn't always from green sources, depending on the grid mix. Some studies estimate the energy consumed by training just one very large language model can be equivalent to the entire lifetime operational energy consumption of several standard office buildings.
Wow. That puts it in perspective.
It does. So we're essentially in a race to find the right balance, the sweet spot. The AI used in building design needs to demonstrably save far more carbon in the built environment over the building's life cycle than the AI itself consumes during its development and operation.
So what's the solution?
It likely involves focusing heavily on optimizing the energy efficiency of the AI hardware itself, specialized chips, more efficient cooling, refining the algorithms to require less computation, and critically, ensuring that the data centers powering these AI tools are themselves running predominantly on renewable energy sources.
Okay. Given this rapid transformation, these risks, the energy paradox, what must architects and designers prioritize learning right now to stay competitive and effective in this changing environment?
It really seems to require a dual approach, mastering new technical skills while simultaneously refining crucial soft skills.
Okay, technical first.
On the technical side, it means moving beyond just basic BIM proficiency towards genuine mastery of advanced, often cloud-based collaborative BIM software. It definitely requires competence in setting up and managing automation workflows within the design process. And crucially, it requires the ability to effectively manipulate AI design inputs.
What does that mean, manipulating inputs?
It means becoming skilled at writing effective, detailed, nuanced prompts to guide the AI. It also means understanding how to accurately tag, curate, and potentially even structure project-specific data sets so the AI can learn effectively and provide relevant outputs for your particular project's context and goals. You need to feed the beast well.
Got it. And the soft skills.
The soft skills are perhaps becoming even more important as differentiators. The first is unwavering design judgment. As we said, not every AI-generated output is viable, desirable, buildable, or ethically sound. Architects need strong foundational knowledge in building science, structural principles, aesthetics, and importantly, ethics, to critically evaluate the AI's suggestions.
Being the critical filter.
Precisely. You also need unparalleled communication skills, the ability to clearly, confidently, and transparently explain these complex, often opaque AI-driven processes to clients, to collaborators, to regulatory bodies who might be unfamiliar or even skeptical about the technology. That skill is becoming absolutely vital to winning trust, getting approvals, and executing projects successfully.
Looking ahead then, the future direction of this AI AEC field seems pretty clear. And the pace of change feels like it's only going to accelerate, doesn't it?
I think so. We can probably expect governments, through both incentives and increasingly stricter building energy codes and environmental regulations, to rapidly mandate further adoption of AI-driven efficiency tools. It might become unavoidable.
Right.
The future evolution will likely see a deeper integration of generative design tools with physical construction technologies, things like construction robotics, advanced prefabrication, large-scale 3D printing, and the Internet of Things, IoT, embedded throughout the building fabric. The goal is to create truly smart, adaptive spaces.
Adaptive.
We are moving, perhaps slowly but surely, toward a reality of more autonomous construction projects. Maybe using robotic assembly guided by AI, and eventually, potentially, self-optimizing buildings. Imagine structures that continuously monitor their internal and external environments and automatically adjust their energy use, their ventilation, maybe even their internal layouts using movable partitions, all in response to changing conditions without needing constant human intervention. The goal is peak green performance optimized over their entire lifespan. #tag outro. So to kind of summarize this deep dive, it seems clear that the fusion of AI and BIM isn't just tweaking things or optimizing design around the edges. It is fundamentally redefining how buildings are conceptualized, designed, built, and operated.
A fundamental shift.
It really is. It's moving sustainable design from being a niche concept or an expensive add-on towards becoming an essential, increasingly standardized tool for achieving ambitious net zero architecture goals. And this is proved by real-world applications we're already seeing across the USA, in operationally intelligent projects like the Edge, and in the pioneering net zero mandate achieved by the Bullitt Center, often with AI assistance in maintaining that performance. Investing in understanding and leveraging this synergy, it's no longer really optional for firms wanting to lead. It seems essential for delivering the sustainable, future-ready built environment we need.
And this brings us perfectly to our final provocative thought for you, the listener, to carry forward from today's discussion. Given that AI can now, or very soon will be able to, rapidly design highly optimized code-compliant buildings in literally minutes, the core value proposition of the human architect seems to be shifting entirely. It appears to be moving away from pure technical proficiency, the ability to calculate stresses, draft complex plans, manage geometry, and moving much more towards ethical judgment, strategic thinking, and the critical definition of the parameters of what should be optimized in the first place. So the question becomes, If AI can increasingly solve the how to build efficiently question with overwhelming speed and power, what critical societal problems, what environmental challenges, what community-based needs are you going to program it to solve next?
That really reframes the architect's role, doesn't it? Thinking about the power in that shift.
Absolutely. Lots to think about there. We'll catch you on the next deep dive.